Section: Introduction. In this section, we discuss how transformer-based large language models, LLMs, are transforming natural language processing. These models have the same setup for each transformer layer, which is called isotropic. While this simplicity is good, it may not distribute parameters effectively within the model. Our work introduces OpenELM, a group of models pre-trained and fine-tuned on public datasets. The key innovation in OpenELM is Layerwise scaling, which optimizes parameter distribution across layers. This technique uses smaller dimensions in the early transformer layers and gradually increases them towards the output. We provide the entire framework, including data preparation, training, fine-tuning, and evaluation processes, along with pre-trained models and training logs to support open research. Importantly, OpenELM performs better than other open LLMs pre-trained on public datasets. For instance, our model with 1.1 billion parameters outperforms OLMO with 1.2 billion parameters by 2.36% while needing half the pre-training tokens. Regarding the model architecture, we use a decoder-only transformer-based design. We follow the latest LLM practices by not using learnable bias parameters in fully connected layers, applying RMS norm for pre-normalization, using rotatory positional embedding, ROP, for positional information, employing grouped query attention, GQA, instead of multi-head attention, MHA, switching the feed-forward network, FFN, with SWI-GLUE FFN, utilizing flash attention for scaled dot product attention, and adopting the same tokenizer as Llama. Unlike traditional LLMs with uniform parameter allocation in each layer, OpenELM varies the configuration of transformer layers to make better use of the parameter budget for improved accuracy. We achieve this by implementing layer-wise scaling, adjusting the number of attention heads and FFN multiplier in each layer. By introducing scaling parameters alpha and beta, we can customize the number of attention heads and FFN multiplier per layer, leading to non-uniform parameter allocation in the model. For pre-training, we utilize public datasets such as Refined Web, Pile, Red Pajama, and Dolma version 1.6, totaling around 1.8 trillion tokens. We perform on-the-fly tokenization and data filtering, which differs from previous methods that use pre-tokenized data. This approach allows for easy experimentation with different tokenizers, simplifying research efforts. We apply character-level and token-level filtering to exclude sequences below specified thresholds of 200 characters and 256 tokens, respectively. Section Summary. In this section, we introduce OpenELM, a family of large language models that utilize layer-wise scaling to efficiently allocate parameters across transformer layers. Unlike isotropic models, OpenELM varies the configuration of each transformer layer, allowing for better parameter utilization and achieving higher accuracies. By adjusting the number of attention heads and feed-forward network multipliers per layer, OpenELM demonstrates superior performance compared to existing models, outperforming OLMO with fewer parameters and pre-training tokens. Section: Training Details. In this section, we trained different versions of OpenELM for 350,000 iterations using CoreNet, formerly CVNets, and AdamW Optimizer. We employed a cosine learning rate schedule with a warm-up of 5,000 iterations and decreased the final learning rate to 10% of the maximum rate. Additionally, we used a weight decay of 0.1 and gradient clipping of 1.0. The training included 4 variants of OpenELM: 270M, 450M, 1.1b, and 3b, some of which utilized FSDP and activation checkpointing. For more details on pre-training, please refer to sec. appendix_pretrain_hyper. For evaluation, we assessed the performance of OpenELM across various tasks using different evaluation frameworks. These tasks included common sense reasoning tasks like ArcEasy and Challenge, BoolQ, HelloSwag, PIQA, SciQ, and Wino Grande. We also considered tasks from Open LLM and LLM 360 leaderboards to comprehensively evaluate OpenELM in terms of reasoning, knowledge understanding, and misinformation and bias. In terms of experimental results, we evaluated the zero-shot and few-shot performance of OpenELM compared to other publicly available language models. We observed an improvement in accuracy with longer training durations across most tasks. Interestingly, averaging the last 5 checkpoints showed comparable or slightly better accuracy than the final checkpoint, likely due to noise reduction through weight averaging. This average checkpoint was used for main evaluations, instruction tuning experiments, and parameter-efficient tuning experiments. Instruction tuning using the ultra-feedback dataset improved OpenELM's average accuracy by 1 to 2% across different evaluation frameworks. Parameter-efficient fine-tuning studies showed that methods like LoRa and DORA can be applied to OpenELM effectively. We conducted benchmarking on modern hardware setups to assess the performance of OpenELM models. Section Summary. In this section, we trained various OpenELM variants for 350K iterations using Cornet and AtomW optimizer with a cosine learning rate schedule. We evaluate the models across different tasks using LM evaluation harness, including standard zero-shot tasks, Open LLM leaderboard tasks, and LLM 360 leaderboard tasks to assess reasoning, knowledge understanding, misinformation, and bias. Our experiments show that OpenELM outperforms existing models, achieving higher accuracy with less pre-training data, and benefits from instruction tuning and parameter-efficient fine-tuning methods. Section: Evaluation. In this section, we present 2 different ways to measure token throughput: prompt processing, pre-fill, and token generation. We also calculate the total combined throughput. To evaluate the models, we run them one after the other, starting with a dry run, where we generate 1024 tokens for the first model to boost the generation speed of the following models. Before measuring each model's performance, we warm up the model by running a single forward pass to allow for any necessary auto-tuning by the frameworks. Throughout all our experiments, we use key value caching and generate 1024 tokens along with the prompt tokens in all tests. We use a static key value cache whenever it is supported. The same prompt, with lengths ranging from 35 to 36 tokens depending on the tokenizer, is used for all runs. The results of our benchmarking on GPU and MacBook Pro are shown in the tables. Despite OpenELM having higher accuracy with a similar number of parameters, we find that it is slower than Olmo. While our main focus is on reproducibility rather than inference performance, we conducted a detailed analysis to identify the bottlenecks. Our investigation reveals that a significant amount of time spent by OpenELM is due to our basic implementation of RMS norm. This implementation leads to multiple individual kernel launches, each processing a small input, instead of a single fused kernel launch as seen in layer norm. By replacing the basic RMS norm with Apex's RMS norm, we notice a notable improvement in OpenELM's throughput. However, there is still a considerable performance gap compared to models using optimized layer norm, partly because OpenELM has 113 RMS norm layers compared to Olmo's 33-layer norm layers, and also because Apex's RMS norm is not optimized for small inputs. To demonstrate the impact of RMS norm on performance, we replaced layer norm in Olmo with RMS norm and observed a significant decrease in generation throughput. In our future work, we aim to explore optimization strategies to enhance the inference efficiency of OpenELM.